Well, thanks everybody for being here today. I'm going to tell you about some of the stuff I've been working on lately. It's really been a very exciting time to be a computer engineer. Unless you've been hiding in a closet somewhere, you've seen the revolution in generative AI taking off. Most of us have spent at least a weekend playing with ChatGPT, asking it to write stories to read to our kids and things like that. And it's amazing how good it is. And I'll try to give you some of the history of that, but I'll probably try to put a little bit more of a twist on it for chip designers. In fact, the general view of this talk is that GPUs have been the enabling technology, both for deep learning and for electronic design automation, both directly, and I'll talk a little bit about how we accelerate some processes like placement and logic simulation, but also how by enabling deep learning, we can then apply deep learning to better and more productively designed chips. So let's go and talk about really where it all started. There are kind of three major ingredients to deep learning. They're the algorithms that I've sort of indicated here by showing the AlexNet graph here at the bottom. There's large amounts of data, either labeled or unlabeled, in this case the labeled data from ImageNet shown at the upper right, and then enough computing power to train a large enough network on a large enough amount of data to make it accurate enough to be interesting. And the first two of these had been around for a long time. Most of the algorithms used in deep learning, deep neural networks, convolutional networks, training them with backpropagation and stochastic gradient descent, have been around since the 1980s. Large labeled data sets came about in the early 2000s. Things like the Pascal dataset and ImageNet were around by at least 2005. But the spark that ignited that air-fuel mixture were GPUs. They were the first time we had enough computing power to train a large enough network on a large enough data set in a reasonable amount of time. And that was AlexNet for image processing in 2012. And it was two Titan GPUs, what we called our Fermi class GPUs, in 2012, running for 2 weeks that trained AlexNet. And since then, the world for image processing has been transformed. The improvement on the ImageNet benchmark that year was more than the improvement in the previous 5 years combined. And moving forward, I think the image processing community did a really good thing in sort of leaving the past behind. The manually designed feature detectors were left behind. And in subsequent years, everybody pretty much moved on to deep learning. Since that point in time, the growth has been phenomenal. Back when we were mostly focused on the convolutional networks for image processing, from 2012 to 2016, there were 2 orders of magnitude growth in the amount of computing horsepower needed to train the neural networks that were leading the pack at the ImageNet competition. And this doesn't really take into account the fact that there were some major developments there that improved the efficiency of these networks, and the move from VGG to GoogleNet, the use of bypass layers and decomposed convolutions were almost an order of magnitude improvement in efficiency, or that graph would have been much steeper. Since the focus shifted to language models in about 2017, the growth has been even steeper, increasing more than an order of magnitude per year. In many ways, what people are able to do is gated by what we can provide in terms of computing horsepower. The big dot at the upper right is my estimate of where GPT-4 is, about 1 million petaflop days of training, or think about that as 1,000 exaflop days of training to train the GPT-4 model now in 2023. So how have we done that? And there are really 2 ways we've tried to meet that growth in demand, this sort of insatiable thing where people could build more powerful models if they had more computing horsepower to train them. And so over the last decade, part of the way we've met that growth is by building more powerful single GPUs. The other way, and I'll talk about that in a minute, is by using more of them together. But remember, we've increased, if I go back a couple slides here, we've increased the demand by 4 orders of magnitude, or just on the language models, and more like 8 orders of magnitude overall. So this 1,000-fold only takes into account part of that need. And this just sort of shows over time how from 2012 with our Kepler GPU to Hopper, which we introduced last year, we have basically gone from about 4 teraops of deep learning inference performance to 4,000 teraops. Let me show you Hopper, and I'll go into a little bit about how that transition happened. So this is our Hopper GPU, shown as an SXM module. The chip and its 6 stacks of HBM memory around it are in the center. I guess I don't have a way of pointing here. The key figure here is the FP8 or INT8 performance, because that's what's used the bulk, both for training and inference of deep neural networks. And the 2/4 number is 2 for dense matrices and 4 for structured sparse matrices. And to feed this, we need 3 terabytes per second of memory bandwidth out of HBM3 memory. And then there are a couple neat features in here. One is something we call transformer engine, which is a special feature put in to accelerate these large language models that scan over the matrices before an operation and determine whether FP8 is sufficient or whether we need to use FP16 accuracy. And then also for accelerating things like bioinformatics, because as much as deep learning is taking over the world, there are other applications. We introduced a number of dynamic programming instructions that make this many orders of magnitude faster than conventional computers at doing calculations on gene sequences. And the key figure of merit is 9 teraops per watt. That's a number I'll come back to when I talk about some things we're going to be doing in the future. And that's a leading number for production deep learning systems today. So how did we get here, and what are the actual innovations that led to this 1,000-fold improvement in performance over the past decade? Well, one thing it hasn't been is semiconductor process technology. In terms of performance per watt, process technologies accounted for about a factor of 2.5, going from Kepler, which was in a 28 nanometer process. And by the way, these are color-coded. Black here is 28 nanometers. The 3 green ones are 16, although some of the later ones, TSMC called 12, it was still 16. And then 7 and 5 nanometer technologies. And so going from 28 to 5 actually gave us about 2.5x in perf per watt. So we didn't get that much out of process technology. It came more from architecture and cleverness. And the two big gains are from number representation and from doing complex instructions to amortize out the overhead of instruction. So for number representations, we built Kepler actually to do graphics and scientific computing. We really, a lot of the time that architecture got nailed down, we were just beginning to play with deep learning at NVIDIA Research. And so we had a limited amount of influence on the product definition of that part. And so its dominant performance was in FP32. That is 4 times the size of the FP8 that we really needed. And because multiply is the thing that dominates the energy, it was 16 times the energy. So 16x was just going from FP32 down to FP8. And along the way, we went to FP16. We found that we could train most networks in FP16 if we scaled them well. I'll talk more about scaling later. For inference, we moved to INT8 in the Turing generation. And in the Ampere generation, we introduced structured sparsity. I'll talk some about that. Then the other big thing that we did was introduce complex instructions. In Kepler, the most you could do by launching one instruction was a fuse, multiply, add. That's 2 operations, a multiply and an add. In the Pascal generation, we introduced dot product, so you do 8 operations, 4 multiplies, 4 adds. But when we introduced the matrix multiply instructions, what the marketing people call our tensor cores, we really got rid of most of the instruction interpretation overhead. So if I scale everything to 45 nanometers, just to make the numbers unbiased by process generation, if all you can do is a fuse, multiply, add, and this is all for half precision, FP16, the overhead is 2,000x. You spend 20 times as much energy fetching the instruction, decoding the instruction, fetching the operand, storing the result, than you do actually doing the arithmetic operations. It's an enormous amount of overhead. By the way, that is very good, right? That's a GPU. On a CPU, it's about 10,000 times overhead because they spend way more effort trying to get good single thread performance, doing branch prediction and register renaming and all sorts of overhead operations that don't actually get any work done. Going to doing the dot products with the very low overhead of a GPU, our overhead was only 5 times, right? All these DARPA people are, and I think of this as the tooth to tail ratio. Our tail of logistics fetching these instructions and stuff is 5 times as much as the payload of actually doing the math. Once we introduced HMMA, which was in our Volta generation of GPUs, the overhead is now only 22%. What this means is you could build a dedicated deep learning accelerator. And by the way, there's some overhead with that too. You still have to fetch your operands from somewhere and put the results somewhere as well. But even if all of that overhead went away, you couldn't do more than 22% better. And that's assuming that you could build as good a matrix multiplier as we can. And we build pretty good matrix multipliers. And with the IMMA for inference, the overhead went down to about 16%. So the other way we have met this increasing demand is by using more GPUs. It became very clear to us when we looked at the size of models, particularly the large language models people were training, that running this on a single GPU was not going to be sufficient. And so we decided we needed to develop networking technology and build the software layers to use it to allow a seamless scale up and scale out. And by scale up, we have a technology we call NVLink and NVSwitch that allows you to build today with Hopper up to 256 GPUs that can do load store instructions to each other's memories over NVLink with essentially no overhead. And it looks like one big GPU, but with 256 times the performance. Of course, there is a bandwidth taper compared to the 3 terabytes per second out of your own HBM memory. And then if you need something larger than that, we acquired a company called Mellanox to allow us to have seamless integration into our InfiniBand networking technology that lets you take those 256 GPU clusters and connect them together up to tens of thousands of GPUs. And today, the big large language models are being trained on clusters on the order of 10 to 20,000 GPUs. These would be the biggest supercomputers in the world if anybody, they would win all of the top 500 contests if people would take the time away from money-making operations like training deep language models to run an HPL benchmark on them. Having this all integrated together means that you can buy what we call a DGX SuperPod of almost any size up to 20 or 30,000 GPUs and plug it in and it works. It's already configured, all the software is already there. There isn't a long and involved bring-up process as it is for most of the big supercomputer acquisitions. Now anybody can build a matrix multiplier. If I assigned it to a graduate student, I'd probably give them a week to come back and have something which looks like a deep learning accelerator with a matrix multiplier at its core. But what makes it useful is layers of software. And so we have, over the past, I think I kicked off the original project that led to cuDNN in 2010. So over the last 13 years, I've been building layers of software, starting with CUDA, our underlying programming system, and many libraries built around CUDA. cuDNN, which is the foundational library that we use for deep learning. On top of cuDNN, our support for all of the popular frameworks, TensorFlow, PyTorch, and all of that, with lots of optimization to make these networks run really fast. And on top of that are end applications running from Modulus, which is where we use deep learning for simulation, at the left side of this slide, to Holoscan, which is a medical application for this at the right side of the slide, and many of the ones in between, including our self-driving vehicles drive. Before I jump into the number representation and how we're going to make this even better, I think one of the key things out of this, and I thought I had the slide in here, but it's not, is if you look at the MLPerf benchmark suite, there's like 100 startup companies trying to do deep learning and many large established companies. Only a few actually bother submitting their results to MLPerf, and it's simply because of that gap in software where they have trouble getting performance results on the benchmarks that matter. They recently introduced an LLM benchmark into MLPerf. And that's really what shows the difference between just having a matrix multiplier and having a whole software stack. Well, my clock is running faster than real time, so I need to move forward. So it turns out that number representation is how we've gotten most of the performance in the past, and we believe there's a little bit more to be squeezed out there, although the low-hanging fruit has been picked, and we're getting up to the upper, very flimsy branches here. And one way to do this is to scale your numbers over a smaller group of numbers. So today what we typically do is we take a whole layer of a deep learning network, we find the biggest and smallest number in that layer, and then we pick a scale factor that takes our number representation and matches it to that range. One experiment we ran, and we did this a couple of years ago, was in MLSys in 2021, is what if instead of having a scale factor for a whole layer, we had a scale factor for every 64 numbers? And the answer is if you do that, you wind up greatly reducing your quantization noise by scaling it and only adding a little bit of extra overhead for these additional scale factors. The other question you can ask yourself is when you're scaling, whether it's a whole layer or a vector of 64 numbers, do you want to scale it so that you can represent the largest and smallest number, or do you want to scale it to a tighter range than that and do some clipping, as shown on the right side of this figure? So it turns out that if you do some clipping, what you're doing, if you look at each of these weight layers here, is you're trading off the noise you introduce by clipping, the uncertainty in representing those outlier elements with reducing the quantization noise. And at the right side of each of these graphs for each of these precisions, you basically have no clipping. And as you move to the left, what you see is the overall noise, the mean squared error, is going down because the amount by which you're reducing quantization noise is more than the amount by which you're introducing clipping noise until you reach a trough. And that trough is the optimum point. You've minimized your mean squared error. And what you see is that if you take that 4-bit line and you trace it over to the trough, you've gained essentially a bit of precision. You're about where a 5-bit line would be with no clipping. So by doing clipping, you're able to better represent by trading off quantization noise with clipping noise. And it turns out you can solve this in closed form by solving the integral on the top there, which unfortunately is quite computationally intensive. But you can actually do a really good approximation iteratively by iterating the function on the bottom. And it basically converges in a couple iterations, and you get a very good clipping factor. So we've taken a couple of these and put them together and have demonstrated a language model running BERT and BERT large on an accelerator that we published last year in the VLSI Circuit Symposium. It's in JSSC this year, and have demonstrated 95 teraops per watt with essentially no loss of accuracy on these language models by doing in 4 bits what most people would have thought would have required 8 bits. And we tend to use, I can't say anything about what will be in our products in the future, but we tend to use these accelerator prototypes as a way of testing out things to put into future GPUs. So let me now talk about, I'm going to run through this really quick in the remaining 3 minutes, how we can take this GPU technology and use it to make better chips. So one way we apply these GPUs directly, this is not deep learning, but it's using a deep learning technique. We're actually using backpropagation to determine the locations of macros and standard cells in a partition that needs to be placed. And so we had a collaboration with the University of Texas and developed a system called DreamPlace that basically uses the deep learning techniques directly to optimize placement. But it wasn't quite doing as well as the industry standard things. So we then put a layer of machine learning, not deep learning, on top of that, using Bayesian optimization for all of the parameters listed in this table here. So for example, one of them is the initial positions of the macros. And if you optimize those positions using a Bayesian method, you wind up getting results that are essentially as good as or better than the state-of-the-art commercial placers, and it runs orders of magnitude faster. Another one, and this is one of my favorites, is we use graph neural networks to predict parasitics. So at one point in time, I did a lot of circuit design, and I would draw a schematic, and it would be handed off to a layout designer, and I would have to wait a day or two for the layout designer to lay it out, extract the parasitics, and then I would find my circuit didn't work because I didn't have a good idea of how much capacitance would be on the various nodes, slowing it down. With this program, we've trained it on a huge corpus of data that we have of circuit designs, and now you can basically take your circuit design, feed it to the neural network, and it estimates the parasitics, and you can see from the correlation plot here pretty well, and you get very, very rapid feedback. You get the design loop closed very quickly and can iterate. Similarly, we do the same thing with routing congestion. You normally have to run the place and route program, which is at least a day, to take a partition and find out where your congestion is. We can do the same thing with the graph neural network and predict where the congestion is going to be in advance. Again, it allows us to iterate more quickly. But in many ways, the most exciting applications of machine learning to chip design that we're doing involve reinforcement learning. One of them is to apply it to our standard cell layouts. We've basically made this where it's almost like playing an Atari game, putting down where the transistors are and connecting them up. So by playing that Atari game, we've been able to build a reinforcement learning program that when we get a new technology, like the 5 nanometer going down to 3 nanometer technology, we can do our new standard cell library, which is about 2,500 cells, in 1 day on 1 GPU. That previously took a team of about 10 people 9 months. This is a wonderful improvement in productivity, and actually the quality of result is better. The cells are smaller and the timing is a little bit better because it does a slightly better job. An even cooler one is designing optimal carry chains. So we do a lot of arithmetic in our chips. Key to arithmetic is a carry look-ahead circuit. And it turns out this is a video game where the object is to pick a place where you're going to put the next look-ahead element to sort of flatten the tree. And if you compare our results running, that's a green line here, running our prefix RL, running a reinforcement learning algorithm to design these carry chains, we tend to do quite a bit better than the typical commercial synthesis tools, reducing the delay from 550 picoseconds to 320 picoseconds for a given size design. And you can constrain it whether you want a really fast design and you're willing to pay some area for that, or whether you want, you can basically constrain either area or speed and have it do the optimum on the other. To wrap up here, we do use large language models like ChatGPT, and we have the advantage that we have a huge corpus of designs, the Verilog code, the documentation, and all of that. And we have internally trained a large language model on more than a terabyte of tokens, and then have fine-tuned it on our own design databases. And we now have a model that we can ask to do things like design the Verilog for a texture interpolator, and it will know what that is and give us a pretty good Verilog design, and can give it all the constraints of what precision and what speed and things like that we want. It's also a great thing to do documentation. It turns out that one of the things that consumes a lot of our senior designers' time is answering questions from junior designers. And so this large language model has been trained on the design database that the junior designer can ask it a question. Most of the time it gets a good answer. So I'm getting a little flashing red lights here, and I think the electric shock comes soon, so I will wrap up. GPUs are the engines of deep learning. They're the thing that ignited the fuel and air of algorithms and data that had been around. And since that point in time, we have been increasing the demand on performance for training neural networks by a couple of orders of magnitude a year, at least in this era of large language models. We've been meeting that goal by both increasing the performance of single GPUs by a factor of 1,000 over the last decade, and also by developing seamless ways to scale up and scale out to tens of thousands of GPUs, because we need to scale on both of those to meet this demand. Using this 4-chip design, we wind up with 1,000x speed up on EDA. I didn't get a chance to talk about logic simulation because I had to shorten this and for the dream place and auto DMP for placement. We can use this as a way of closing our design loops much more quickly, allowing designers to not have to wait a day to get a result and iterate their design, but do it in a few minutes by doing things like doing design rule checks, finding hotspots, parasitic estimation, looking at power density, looking at routing congestion. And then the thing that's really exciting is using reinforcement learning to get superhuman designs, things like those carry chains, which no human would ever design and are better than the human designed ones, and better productivity, because we can turn these things around doing what took a group of many people 9 months to do, we can now do overnight on one GPU. And then finally, the large language models are a way of taking our combined knowledge base of designs on GPUs and putting it in something where junior designers can ask questions, we can ask them to do the design, and it greatly leverages the productivity. We don't have any quantitative measures today, but I guess we're already to the sort of 1.2 level, and I would hope that we can get to 2x, basically get a single designer to be twice as productive as they were using these models. So this is where I live. Thank you very much for your time, and have a great day.